Okay, 2.30 wants us to normalize the wave function in equation 2.154. Now, for reference, the equation that's being talked about here is the even wave function for the finite well, psi of x being a piecewise of f e to the negative kx when x is greater than a, d cosine of lx between a and 0, and then psi of just negative x, which is exactly symmetrical across when x is less than 0. So our goal is then to determine the constants d and f in terms of all the other constants provided. So to do that, the first thing we have to do is we have to define everything in terms of a single coefficient. And then after that, we have to define that coefficient in terms of all of the constants. So let's suppose that we want to express everything in terms of d. So we have the continuity equation, which is that at x equals a, f e to the negative ka has to equal d cosine of la. And from here, we can say, okay, f is then equal to d e to the ka times cosine of la. So if we plug this in, then our new wave function piecewise equals, let's see, this is going to be d times e to the ka times cosine of la multiplied by e to the negative kx when x is greater than a, and then we just have d cosine of lx when x is between 0 and positive a, and then we have psi of negative x on the other side. So from this point, we just have to normalize this. So to do that, one of the things we can do to make this a little bit easier on ourselves is we can take advantage of symmetry. Remember that this is an even functions are symmetric. So all we really have to do, instead of integrating from negative infinity to positive infinity, we can just integrate from 0 to positive infinity and set that equal to exactly 1/2, instead of doing the whole thing and setting it equal to 1. So we can say 1/2 is equal to the integral from 0 to positive infinity of the magnitude of psi of x squared dx. There's no imaginary terms here, so we can just do this right away. 1/2 is equal to the integral from 0 to infinity of, let's see, we actually have to split this up. So this is going to be equal to, let's see, from 0 to a of d squared cosine squared lx dx, and then we're adding the integral from a to infinity of d squared e to the 2ka cosine squared la times e to the negative 2kx dx. And immediately, what I see here is this is a cosine squared term. We have to use trigonometric identities. Angle formula. Let me just double check this. Yes. So immediately, to do this first integral, we have to take advantage of double angle. So this is going to be d squared times the integral from 0 to a of cosine squared lx dx. And then I can make the realization that cosine of 2 times something, 2 times a, is equal to 2 cosine squared times a minus 1. So in that case, 2 cosine squared times a is equal to 1 plus cosine of 2a, or cosine squared of a is equal to 1/2 plus 1/2 cosine of 2a. From this point, if we want to replace a with lx, then we have cosine squared of lx is actually equal to 1/2 plus 1/2 cosine of 2lx. So in reality, this becomes d squared times the integral from 0 to a of 1/2 plus 1/2 cosine 2lx. So going back to black, our general formula is going to be 1/2 is equal to d squared multiplied by the integral from 0 to a of 1/2 plus 1/2 cosine 2lx dx. And then we're adding e to the power of 2ka times cosine squared la, integral from a to infinity of e to the negative 2kx dx. And this is just an integral we can just arbitrarily do. So let's do this. 1/2 is equal to d squared. Let's see. This is going to be 1/2 x plus 1/2 sine 2lx times 1 over 2l. Is that correct? Yes. And then this is evaluated from 0 to a. And we're adding e to the 2ka times cosine squared la times e to the negative 2kx multiplied by 1 over negative 2k. And this whole thing is, this whole thing is evaluated from a to infinity. Close off this bracket. And then we have 1/2 is equal to d squared. And then let's see, this is going to be 1/2 x plus 1 over 4l sine 2lx. And then we're adding, let's see, negative. In fact, you know what? Let's move the negative out to the front here so that everything's a little bit simpler. We're subtracting e to the 2ka over 2k cosine squared times la e to the negative 2kx, evaluated from a to infinity. And now if we actually do this, and I forgot to do the bar symbol here from 0 to a, okay, 1/2 is then equal to d squared multiplied by, let's see, this is going to give us 1/2 a plus 1 over 4l sine of 2la subtracted by 0 subtracted by 1 over 4l sine of 0. So sine of 0, that's just 0. So everything here goes to nothing. And then next we're subtracting by, let's see, e to the 2ka. So first off, the first term at the front here is e to the negative infinity, which is automatically 0. The second one is going to be minus e to the 2ka over 2k times cosine squared la e to the negative 2ka. Closing all of this off. From this point, then 1/2 is equal to d squared times a over 2 plus sine 2la over 4l added with e to the 2ka over 2k times cosine squared la times e to the negative 2ka. So the e to 2ka and e to the negative 2ka cancel out to 1. So those automatically go away, and then we can move the cosine squared to the top of the fraction. So this leaves us with cosine squared la. From this point, let's see, we can multiply the 2 over, then 1 is equal to d squared of a plus sine 2la over 2l plus cosine squared la over k. We can combine everything if we want, so this is going to give us 1 is equal to d squared times 2la plus sine 2la over 2la plus cosine squared la over k. Combining this final fraction, we get that 1 is equal to d squared multiplied by 2lak plus k sine 2la plus 2la cosine squared la divided by 2lak. I feel like there isn't supposed to be a cosine squared here. Cosine squared, cosine squared. DE. No, this is right. Apologies. Just got a bit paranoid there. Okay, 2lak, and then after that we switch everything around. D squared is equal to 2lak plus k sine 2la plus 2la cosine squared la, and then all of this is with 2lak at the top. And at this point, we can make this a little bit nicer by dividing everything by 2lak. So d squared is actually going to equal. So this is at the bottom. let's see. Did I do something wrong? 2LAK. (2LA) over... I did do something wrong here. There's not supposed to be an A here. So there's not supposed to be an A here. This is supposed to be just 2LK, in which case there's not supposed to be an A here either. So this is just 2L. My apologies. Move everything over. This is 2LK. And then at the bottom we have 2LAK plus K sine 2LA plus 2L cosine squared of LA. Okay, yeah, that looks more like what it's supposed to. Okay, apologies. Now, we divide everything by 2LK, and what we get is at the bottom, this is going to become A plus, let's see, 1 over 2L sine 2LA plus 1 over K cosine squared LA. And then everything at the top is just divided and becomes 1. So then D is just equal to square root of A plus 1 over 2L sine 2LA plus 1 over K cosine squared LA. Mark off the square root. Fraction at the top. Erase this accidental mark. And at this point, technically, we have finished. However, the reason why I'm saying technically is because this is still kind of too general of an equation. And the reason why it's still too general is because we haven't actually employed the second condition for continuity yet. So far, everything has been solved using only the continuity expression for psi itself. We still have the continuity requirement for the derivative of psi. So if we look back, right, we have fe to the negative ka equals d cosine la, but we still have sort of the second condition that we need to sort of imply in this resulting equation. So we have the continuity of psi. We still need a continuity of the derivative of psi. So what we still need to incorporate is negative. Let's see. This is negative k at the front. Negative k times f times e to the negative kx, or ka, has to be equal to negative L d sine of LA. So we haven't incorporated this yet. And if we look down here, let me just copy paste this and move it over. If we look down at what we have already, doesn't really seem to be an easy way to sort of incorporate this condition, because the second condition is like in terms of f and d, and there's no f in here anymore. Everything's only in terms of d. However, one easy way to sort of incorporate this is we can remember that if we combine these two expressions, we get a condition for k and L. And we can do that, and then we can either express L purely in terms of k or express k purely in terms of L, and that would sort of indirectly incorporate our second condition. So if we do that, divide, this second expression by the first expression, then what we get is that negative k is going to equal negative L times sine of LA over cosine of LA, where I'm taking this as the numerator, I'm taking this term as the denominator. So this gives us an expression for k. Getting rid of the negatives, this just k equals L sine LA over cosine LA. And at this point, we have a way to incorporate or express k in terms of L, or L in terms of k, either or, and this indirectly incorporates the second continuity expression. So if we plug this into here and rewrite it in terms of either just L or just k, this would actually give us a more accurate, technically, because this is still right. It's just too general. It doesn't include sort of this second condition. So by doing this, we're specifying the equation a little bit more and adding some more constraints. So if we do that, more generally, it makes more sense to define L in terms of K, because K is what actually matters. It determines our energy, so it makes less sense to define things in terms of L and more sense to define things in terms of K. So if we do that, then L is equal to K times cosine of LA over sine of LA, in which case D is now equal, with the bottom being, let's see, A plus 1 over 2L sine 2LA. And if we express L in terms of K, then let's see, 1 over L is going to become 1 over K times sine of LA over cosine of LA. So if you get rid of 1 over L and turn it into 1 over K, and then times sine LA over cosine of LA. And then we are adding 1 over K cosine squared LA. And then everything at the top is just 1, and we're square rooting everything down here. This is a very messy square root, I'm sorry. And next, we can once again take advantage of double angle, because if we recognize that like sine of, if we recognize that, let's write this in purple, via double angle, sine of 2LA is actually equal to just 2 sine LA times cosine LA, then what D actually equals is, let's see, this is going to be A plus 1 over 2K times 2 sine LA times cosine LA multiplied by sine LA over cosine LA plus 1 over K cosine squared LA. And then we take the square root of everything here, take a fraction, and then 1 at the top. Instantly, the 2's cancel, the cosines cancel. What we have left is D is equal to, at the bottom, A plus 1 over K sine squared LA plus cosine squared LA. Take the square root of everything. This is the denominator. Instantly, this is just equal to 1, so D is now equal to 1 over square root of A plus 1 over K. And this is the actual, more specific, more quote-unquote correct answer for D. And now that we have D in terms of constants, we can plug this back into F, because if we look up here, we know that F is equal to D times e to the Ka times cosine of LA. So if we plug in D, this is actually equal to, this is going to be equal to e to the Ka over the square root of A plus 1 over K multiplied by cosine of LA. And with that, we are done with this problem.